Yeah, in this video, I'm going to discuss about how to write the cyclic structure of glucose and why the cyclic structure of glucose has been proposed. Um, yes, let us see. Yes, you know the molecular formula of this glucose is how much? I mean, what C6H12O6, right? First of all, let us write the open chain structure of glucose. This is the open chain structure of glucose, right? Where we have CHO at first position and CH2OH at the bottom and HOH, HOH and number them, right? 1, 2, 3, 4, 5 and 6 carbon atoms. Only at the third carbon atom, the configuration is just the reverse. Otherwise, the H and OH is on the left and right? This is the open chain structure of glucose. But this open chain structure of glucose could explain many of the properties, but it could not explain few of the properties like, yes, like it does not give shift test, right? It does not give shift test, that is, it is not giving the shift test, and also it does not give hydrogen sulfide addition product, does not give the hydrogen sulfide addition product with sodium bisulfite, right? And also it does not explain, I mean, the pentaacetate which is formed here after, I mean, when glucose, this is the structure of glucose, that is open chain structure of glucose, and when it reacts with acetic anhydride, here it gives pentaacetate. This pentaacetate does not, I mean, the pentaacetate which the glucose forms after it reacts with acetic anhydride, the pentaacetate which is being formed here does not react with hydroxylamine. Right, this is a hydroxylamine, no reactions. So it is not going to give the Chef's test positive. It does not give an addition product with sodium bisulfite, and also the pentaacetate of this glucose which is being formed after its reaction with acetic anhydride does not react with hydroxylamine. All these are the characteristics of this aldehyde group. So, which means that the aldehyde group is not free in this glucose. That means, so we can propose that this aldehyde group is not free, so a cyclic structure has been proposed. So we can get the cyclic structure in order that, I mean, in order to explain the properties here, whether it's not giving shift test, it's not forming an addition product, the pentaacetate is not reacting with hydroxylamine, all this can be explained when we propose that the CHO group is not free, instead it is involved in the ring formation. Yes, so how this is involved in the ring formation here? Yes, the OH group which is present on the fifth carbon is involved in the ring formation with CHO group. This carbonyl. So we'll get what 6-membered ring is observed here. 6-membered ring. Okay, so now here so since open chain structure is unable to explain, this is open chain structure. Once again, I'll draw here quickly. This is CHO, CH2OH, HOH, HOH. Okay. Since this is unable to explain all the properties, so the cyclic structure has been proposed where the the OH group which is present on the fifth carbon atom is involved in the ring formation with this carbonyl group, right? And thus results in the formation of two forms here. That means alpha and beta forms. Both are crystalline forms here. So now glucose now found to exist actually experimentally in two crystalline forms, which is alpha and beta, and both of them are obtained from this glucose only, that means open chain structure of this glucose by crystallization of this at different temperatures. So if we crystallize this at a temperature of about 303 Kelvin, then we'll get alpha glucose. And at what temperature? This is at 371, no, yeah, 371 Kelvin. I mean, by by the crystallization of this glucose at 371 Kelvin, we'll get the beta form. And the melting points of this alpha form and beta form are different. The melting point of this is 419 and this is 423. So both of them, I mean, the glucose now experimentally has been found exist in two forms, it is alpha and beta forms. Both of them are obtained by the crystallization of this glucose at different temperatures, and the melting points of alpha glucose and beta glucose are also different, where it is 419 Kelvin and 423 Kelvin. So now the cyclic structure, I can write the cyclic structure of this. See how I'm writing. First carbon, here, put first carbon, draw this vertical line and 4 lines here. Okay, 4 lines. See, and now this carbon is involved in the ring formation with the 5th carbon, right? Number them 1, 2, 3, 4, 5, and 6th carbon is the CH2H. You know this, right? Now this is involved in the ring formation with this, right? So the oxygen in, so how many atoms are there? So I fill in this now. This is the first carbon atom. So this H will go there. This is OH, H. Second, also the same thing. Only thing is reverse the configuration at the 3rd carbon atom. 4th is also the same thing. And 5th also H. Right? Now, this is the structure of alpha. This configuration is D as we know, and this is dextrorotatory alpha D glucose. This is the open chain structure. And now, I mean, I'll write the beta structure also. Now, you can see how many member ring? 1, 2, 3, 4, 5, 6 member ring. So 6-membered ring is being formed, right? And this is called a cyclic hemiacetal structure. What is this structure called as? These two cyclic hemiacetal structures. And how do I write the beta form? Same as alpha, only thing is at C1 carbon atom, you inverse the configuration. Same as alpha, only at C1 carbon atom, the configuration is different here. So I'm writing C here, which is the first carbon atom. Put 4 lines here, and last carbon atom is CH2OH. That is 1, 2, 3, 4, 5, and 6, right? Now, this is involved in the ring formation with the 6th OH. So, O is there in the ring, in the 6-membered ring. So, only thing is, I'm reversing the configuration at the first carbon atom, H and OH. Rest all is things, H, OH. At the 3rd, again, inverse, reverse, I mean H, OH, and this is H. This is of what? Beta. Its configuration is D because at the bottommost carbon atom, which is linked to CH2OH, the H is on the left side and is dextrorotatory and then glucose. So this is alpha glucose and beta glucose, and how to write these structures also. Right? This is how you write the structures of alpha glucose and beta glucose, and these are called as what? Cyclic hemiacetal structures. And these are called as anomers, that means differing at the configuration at only one C1 carbon atom, right? This OH functional group is towards the right and towards the left here. This is carbon is called as an anomeric carbon and differing only at one carbon configuration, so called as what? Anomers. These two are called as anomers. So these two are called as what? Anomers. Because they are differing in the configuration only at C1 carbon atom called as anomeric carbon atom, that is the, I mean, with reference to OH. Right. This is how the cyclic structure has been proposed to explain the few properties of glucose which otherwise could not be explained by the open chain structure. And this is called as what? Fisher projection formula. And how to write the Haber projection formula, I'll also explain that. Yes. Here, from the Fisher projection formula, we can write the Haber projection formula. And this one, if you can see, the 6-membered ring is in analogy with the pyron. This is pyron. The 6-membered ring, 5 carbon atoms and oxygen in the cyclic structure. Also, we have the same structure. I mean, 1 oxygen and 5 carbon atoms. That is why they are called as pyranose structures. So alpha and beta forms are also called as what? Pyranose structures. Right. How to write this Haber projection? Just write this 6-membered ring with oxygen. Here, I'm writing the alpha here, D plus glucose. And these are what? Haber projections. Haber projection formula. Haber projection formulas. Here, write a 6-membered ring with oxygen here and put vertical lines across every carbon atom. So number them. This is 1, 2, 3, 4, 5, and 6th carbon atom here will be here. I'll write. So, the atoms which are present in the Fisher projection formula towards the left and right, here we'll write up and down here. That's it. Right. So at first carbon atom, we have H and OH on the left and right. So we have up and down. Second, also the same thing. Third, just reverse it. Fourth, also the same thing. Fifth and 6th, right? The 6th carbon atom, H2H and H. This is what is for alpha. And beta is the same here, only thing is differing at the configuration at the first carbon atom, right? That is what is beta. So I'll write everything same, number them 3, 4, 5 and 6th carbon atom. Only thing is differing configuration at C1. That is the anomeric carbons, OH, H, H, OH. Second, third is just the reverse and H, OH, and this is CH2, OH, and H. This is beta, D plus glucose. Dextrorotatory and plus here for dextrorotatory. Yes, it is D notation. This is how you write the Haber projection formula from the Fisher projection formula for glucose alpha and beta glucose. This is a simple way of writing the structures of glucose. If you like it, please do like, share, and subscribe my channel. The whole chapter has been discussed on my YouTube channel, and the details of it has been given in the description box. Yes. And if you want the video to be made on any particular topic, please share it in the comment section.